if I have a function y equal to fx, and fx is continuous everywhere, say y equal to fx, and fx is continuous everywhere, y equal to fx and fx is continuous everywhere. Say in its domain, there is a point x equal to a where the function changes sign. Fa is 0. Is 0. Fx changes sign at x equal to a. To the left of a and to the right of a, immediate left of a and to the immediate right of a, the function has opposite signs. Let's say such be a function, right? Now, if I look at y equal to mod of fx, right? If I look at y equal to mod of fx, hey, y equal to mod of fx, if you recall, I had discussed this, mod of fx will be the same as fx whenever fx is greater than or equal to 0, and will be minus fx whenever fx is less than 0. That means fx is greater than or equal to 0 in this case for x greater than or equal to a. Fx is greater than or equal to 0 when x is greater than or equal to a, yes or no? Fx is less than 0 when x is less than a. Therefore, to the right of a, mod fx and fx are identical, right? The graph of y equal to fx and y equal to mod of fx to the right of a are the same, right? To the right of a, fx is the same as mod fx. Mod fx and fx enjoy the same y's, same values for any x to the right of a. But to the left of a, if this is fx, then mod fx would be minus fx. To the left of a, this is fx for any given x, but mod fx would be minus fx. That means for any given x, if this is the value of fx, then mod fx would be minus fx. This would be minus fx, and this would be mod of fx. That means if this is a point on the graph of fx, then this would be a point on the graph of mod fx. And do you realize p and p prime are mirror images of each other about the x-axis? That means if this is the graph of y equal to fx to the left of a, the graph of mod of fx to the left of a would be obtained by reflecting this about the x-axis. Reflecting this about the x-axis. So reflect this about the x-axis. This then would be the graph of y equal to mod of fx. Yes or no? The portions in which fx is positive, retain that portion. The portion where fx is negative, reflect that portion about the x-axis. Together it will give you the graph of y equal to mod of fx. How about it? Right? Now, fx was a good function. It enjoyed continuity at x equal to a. And in fact, it also enjoyed differentiability at x equal to a. But look at mod fx. It did not get touched on it on the right hand derivative. The right hand derivative at x equal to a of this was the same as the right hand derivative at x equal to a. But the left hand derivative now became this. So then differentiability was lost. Differentiability was lost. Yes or no? Although my disclaimer is, if there is a function y equal to fx and it is continuous and differentiable everywhere, it is continuous and differentiable everywhere, at x equal to a fx changes sign, then mod fx is vulnerable to loss of differentiability at x equal to a. it could lose differentiability at x equal to a. Doesn't mean that it will necessarily lose differentiability at x equal to a. I mean, you could have had something like this, for example. Fx could have been like this, say. It changes 0 at x equal to a, and it changes sign at x equal to a, say. So this is the graph of y equal to fx, right? This is the graph of y equal to fx. It is continuous at x equal to a, and its tangent is this. Slope of the tangent is 0 at x equal to a. Now if I have to draw the graph of y equal to mod of fx in and around x equal to a, to the right of a, it will retain the same graph. To the left of a, this portion will get reflected. This portion will get reflected about the x-axis. Like this. And differentiability is not lost. And differentiability is not lost. See, this is the graph of y equal to mod of fx, and differentiability is not lost. So then the rule of the game is that if fx be continuous and differentiable at x equal to a, mod fx will still be continuous at x equal to a, but may or may not lose differentiability. It loses differentiability in this case, for example, but it does not lose differentiability in this case. Yes or no? Right? So x equal to a would be a point of contention, a point of investigation for y equal to fx. If fa is 0 and the function changes sign around x equal to a, then mod fx, if it itself is continuous at x equal to a and differentiable at x equal to a, must be investigated with due respect. Clear? Can I wipe this off? Say, for example, y equal to fx equal to mod ln x. This will be equal to ln x whenever ln x is greater than or equal to 0, that is when x is greater than or equal to 1. Is ln x when x is greater than or equal to 1, and is minus ln x when ln x is less than 0, that is x less than 1. Yes or no? Now, so at x equal to 1, it changes character. To the right of 1, it behaves like ln x. To the left of 1, it behaves like minus ln x. Minus ln x, right? So x equal to 1 must be checked for continuity and differentiability, right? So first of all, continuity. Limit fx, x tends to 1 from the less than 1 side. When x is less than 1, it's described as minus ln x. So this is limit minus ln x. X tends to 1 from the less than 1 side. That's 0. Left hand limit is 0. Whereas limit fx, x tends to 1 from the greater than 1 side, is like limit. When x is greater than 1, it's described as plus ln x. X tends to 1 from the greater than 1 side, that's 0. So the left hand limit is 0, right hand limit is 0. The value of the function at x equal to 0, at x equal to 1, the value of the function at x equal to 1 is also 0. Put x equal to 1. So the function is continuous at x equal to 1. Left hand limit at 1 is equal to the right hand limit as 1 is equal to the value of the function at x equal to 1. So continuous, all right. The function is indeed continuous. So I need to check it for differentiability at x equal to 1. Now, f dashed 1 plus 0, right hand derivative at x equal to 1. That's going to be limit fx minus f1 by x minus 1 as x tends to 1 from the greater than 1 side. When x is slightly greater than 1, fx is ln x, f1 is 0, x tends to 1 from the greater than 1 side. Yes or no? This limit? Which is like limit ln 1 plus x minus 1 by x minus 1 as x tends to 1 from the greater than 1 side. As x tends to 1, I hope you realize what I did here. As x tends to 1, x minus 1 tends to 0. So ln 1 plus something by something as something tends to 0 is 1. So this is 1. So the right hand derivative, slope of the right hand tangent is 1. Whereas slope of the left hand tangent 1 minus 0 is limit fx minus f1 by x minus 1 as x tends to 1 from the less than 1 side. When x is less than 1, its description is minus ln x. f1 is 0 by x minus 1 as x tends to 1 from the less than 1 side. In exactly the same way, you write this x as 1 plus x minus 1. It's the same as this except that there is a minus sign appearing and this limit would be minus 1. So the slope of the left hand tangent is minus 1, slope of the right hand tangent is plus 1. The function is not differentiable at x equal to 1. At x equal to 1, it has two distinct tangents. Uniqueness of tangency does not prevail at x equal to 1. The function is not differentiable at x equal to 1. It's not derivable at x equal to 1. Yes or no? Right? In a graphical perspective, let me look at it in a graphical perspective. I don't have to use algebra all the time. I can use a graphical approach for a typical situation, right? Although in your school exam or in your board exams, by and large adopt an algebraic approach. They prefer that for a school exam or for a board exam. Stick to that. In most cases, that'll work. Can I wipe this off? Graphically, say this is the graph of y equal to ln x. At x equal to 1, it changes sign. Right? This is the graph of y equal to ln x. And it's a good function at x equal to 1. Both the properties of continuity and differentiability are properly met. The derivative at x equal to 1 would be plus 1. Slope of this tangent at x equal to 1 would be plus 1 for ln x. Slope would be plus 1. The slope of the tangent at x equal to 1 would be plus 1 for y equal to ln x. Left hand tangent is also plus 1, right hand tangent is also plus 1. They flush together. It's differentiable at x equal to 1. Now, if I draw the graph of y equal to mod ln x, wherever ln x is positive, you retain the same portion, right? This is the, wherever negative, you have to reflect this portion about the x-axis. Ln x is negative here. You reflect this portion about the x-axis to this to get this portion. Yes or no? Yes. Right? And now, there you see. The right hand tangent remains the same, but the left hand tangent becomes this. A sharp corner has been produced and the function has generated a point of non-differentiability. Lack of differentiability, non-uniqueness of tangency has been produced at x equal to 1 by taking modulus of ln x. Right? In fact, what has happened is, while this portion got reflected, this goddamn tangent also got reflected like this. Yes or no? So reflection of this tangent y equal to x, tangent of slope 1 will produce this tangent of slope minus 1. That is what happens. You know what I'm saying? Clear? Now, another important transformation with which we will have to deal with time and again. Say someone gave you the graph of y equal to fx. Someone gave you the graph of y equal to fx. So this was the graph of y equal to fx versus x. I now want to be able to draw the graph of y equal to f of mod x. I now want to be able to draw the graph of y equal to f of mod x. Yes or no? Now, if I look at this f of mod x, whenever x is greater than or equal to 0, mod x will be the same as x. Whenever x is less than 0, mod x will be the same as minus x. That means for a given x, the y that I get is the same as the y that I get out of minus x. I'll explain. Okay. In f of mod x, the value of this function, the value of y at x equal to plus 2 would be what? 2. Right? This is the value of this function at x equal to 2. The value of this function at x equal to minus 2, mod of minus 2, that will also be f2. Yes or no? That means for x equal to 2, if I am getting a certain y equal to y naught, then for x equal to minus 2, I am getting the same y naught. If for x equal to 2, y will be y naught, will be a point on the graph of this function. X equal to minus 2, y will still be y naught. This is also a point on the graph of the function. Yes or no?
Yes, sir.
In a very general sense. Similarly, if I had a certain x producing a certain y, if I had a certain x producing a certain y, then a minus x will produce the same y, right? Then that means if a positive x is producing a certain y, then negative of this x will produce the same y. Even, of course, but yes, surely even, which means if x comma y be a point on the graph of the function, then minus x comma y will also be a point on the graph of the function. If x is a positive number and x comma y be a point on the graph of the function, then minus x comma y will also be a point on the graph of the function. Yes or no? But these points P and Q are what? Mirror images of each other about the y-axis. Mirror images of each other about the y-axis. Yes or no? If x comma y be a point on the graph of the function, then minus x comma y will also be a point on the graph of the function. And P and Q are mirror images of each other about the y-axis. Yes or no? Right? That means this function will exhibit symmetry about the y-axis. This function will exhibit symmetry about the y-axis. Yes or no? Which means if I had knowledge of the graph of the function to the right of the y-axis, if I had knowledge of the graph of the function to the right of the y-axis, Then all that I need to do is reflect this about the y-axis. This along with its reflection about the y-axis will give me the graph of y equal to f of mod x. Yes or no? You know what I'm saying? That means now if I have to draw the graph of y equal to mod of fx, f of mod x, all that I need to do is retain the portion to the right of the y-axis and reflect this portion to create its mirror image about the y-axis. These two are mirror images of each other about the y-axis. This will be the graph of y equal to f of mod x. Yes or no? Huh? Which means say y equal to ln x versus x was like this, right? This is the graph of y equal to ln x versus x, right? If I have to draw the graph of y equal to ln of mod x, no. If I have to draw the graph of y equal to ln mod x, retain the portion to the right of the y-axis and reflect it about the y-axis. Realize that ln x was defined only for x greater than 0, but ln mod x is defined for all x. Because no matter except x equal to 0, it's defined for even negative values of x. Because if x is negative, mod x will still be positive. So this would be the graph of y equal to, I have not drawn a complete mirror image because I'm poor at drawing. You might want to draw it better. This is the graph of y equal to ln mod x. So from fx to f mod x, what would you do? Retain the portion of fx to the right of the y-axis and reflect the damn thing about the y-axis. The portion to the right of the y-axis along with its mirror image to the left of the y-axis will together constitute the graph of y equal to f of mod x. F of mod x. Yes or no? Now, suppose I want to draw the graph of mod of ln of mod x. See, wherever negative, reflect it about the x-axis. This will be the graph of mod of ln of mod x. See, if I have to take the mod of this, wherever this is positive, I retain that portion. Wherever negative, I reflect it about the x-axis. This then would be the graph of mod of ln x. Yes or no? And you see that mod of ln x is discontinuous at 0, continuous everywhere, but not differentiable at plus minus 1. Not differentiable at plus minus 1. Right hand derivative, left hand derivative. Yes or no? Right? All's good? Straightforward, right? Can I wipe this off? No issues, right? You came in very late, Shashi, today. Where were you stuck? Okay, we'll talk about that later. Now, say y equal to sin x. This is the graph of y equal to sine x, right? And so on and so forth. This is the graph of y equal to sine x. Okay. Let me draw the graph of y equal to sine mod x. Let me draw the graph of y equal to sine mod x. F mod x, that is, right? So retain the portion to the right of the y-axis. Right? Retain the portion to the right of the y-axis and reflect this portion about the y-axis. So if you reflect this portion about the y-axis, this. At x equal to 0, sine x was differentiable as well as continuous, but at x equal to 0, sine mod x maintained continuity but lost differentiability. So sine mod x, as you can see, sine mod x is not differentiable at x equal to 0. Graphically you can see that, right? But it's continuous and differentiable everywhere else. At x equal to 0, it's still continuous but loses differentiability. It now enjoys two distinct tangents at x equal to 0. I am not sure how much it enjoys that. So algebraically, if I had to establish differentiability or lack of it for sine mod x, fx is, say, sine mod x, right? F dashed 0 plus right hand derivative at x equal to 0 would be limit fx minus f0 by x minus 0 as x tends to 0 from the greater than 0 side. When x is slightly greater than 0, mod x will be x. f0 is 0 by x as x tends to 0 from the greater than 0 side, which is the right hand derivative at x equal to 0, limit sin x by x, that's going to be 1. Right? Right hand derivative at x equal to 0, whereas left hand derivative at x equal to 0, f dashed 0 minus 0 is limit fx minus f0 by x minus 0, x tends to 0 from the less than 0 side. When x is less than 0, mod x would be minus x, sin minus x would be minus sin x. I hope you realize what I did here. Fx would be sin minus x, which is minus sin x, and that's going to be minus 1. So the left hand tangent has slope minus 1 and the right hand tangent has slope plus 1. As you can see, the function is not differentiable at x equal to 0. Clear? In contrast, say this is y equal to fx equal to cos x. This is y equal to fx equal to cos x. Yes or no? if I have to draw the graph of cos mod x? Yes, because this already is the mirror image of this. So if you retain this and reflect this very portion about the y-axis, it matches with this. In this case, f dash 0 will be 0. Slope of this tangent will be 0. Slope of this, the tangent drawn at x equal to 0 will have slope 0, right? And cos mod x will have the same graph as cos x. So cos mod x is differentiable at x equal to 0, whereas sin mod x is not differentiable at x equal to 0. Clear? Easy to see. Say f dashed 0 plus 0, let's say right hand derivative, limit cos mod x minus cos 0 is 1, right? Value f0 which is 1, fx minus f0 by x minus 0 as x tends to 0 from the greater than 0 side. That's the right hand derivative at x equal to 0, fx, and f0 is 1 by x minus 0. fx minus f0 by x minus 0, x tends to 0 from the greater than 0 side. When x is slightly greater than 0, mod x will be x. So this is going to be limit cos x minus 1 by x as x tends to 0. Yes or no? Which is going to be minus twice limit sine square x by 2 by x as x tends to 0. Right? Yes or no? Which is going to be minus twice sine x by 2 divided by x by 2 whole square by 4 into x as x tends to 0. Yes or no? This will tend to 1, this tends to 0, so this is 0. So the right hand derivative at x equal to 0 is 0. And similarly, left hand derivative, that is f dashed 0 minus 0 is limit. I'll have same thing, x tends to 0 from the less than 0 side. Mod x will still be x. When x is slightly less than 0, mod x will be minus x, but cos minus x will be the same as cos x. So this is like limit cos mod x minus 1 by x as x tends to 0 from the less than 0 side, fx minus f0 by x minus 0, right? X is less than 0, so mod x is the same as minus x. But cos minus x is the same as cos x. And this, like before, will be 0. Yes or no?